Design of low leakage low voltage high density 6T-SRAM bit cell. Abstract. A low retention voltage 6T static random access memory is analyzed in 40 nm CMOS technology and standard 6T-SRAM with high threshold voltage transistor for ultra-low leakage is used with area of used 6T-SRAM is 0.242 UM2. In this work we reduced the rail-to-rail swing of 6T-SRAM cell by increasing the ground voltage, which will decrease the leakage current at worst corner FF/125 of memory cell. And also introduction. In today's scenario, we are decreasing the size of transistor to make a compact design through which we can perform numerous of operations and also follow the Moore's law. Also we can increase the density of chip through which reduce the cost of the fabrication, but same power density also increases which restrict the size of die 1. Due to technology scaling, some parameters of the device also fluctuates like gate oxide thickness, length, and varied the some device characteristics. To reduce the power density of the chip by reducing the supply voltage and threshold voltage, performance of memory is deterioration due to some unwanted parameters like sub-threshold voltage, reverse diode leakage and power dissipation, which decreases the performance of SRAM like stability and restrict the high-speed applications too. But where less speed is required we can reduce the supply voltage. SRAM suffers from parametric variations due to smallest geometric size of SRAM cell. Stability of the memory read is decided by static noise margin, SNM, or read margin, RM. Retention stability is decided by the retention noise margin, RNM, and write stability of memory is decided by write margin, WM. Generally there are numbers of architectures of SRAM through we can use read and write operation of memory cell, but most commonly used architecture is 6T-SRAM memory cell because its nature of very high density. With the help of this we can increase the size of memory on a single chip. Area and power consumption is two major part of system on chip, SoC, because 20 to 30% of area is occupied by the SRAM and 40 to 50% of total power of chip is consumed by the SRAM. But sometimes due to parametric variations there is a need to use 8T and 10T SRAM memory. For low power consumption need to scale down the supply voltage, but this will impact on the stability of the memory cell. Scaling the Fig 1. 6T SRAM cell. Supply voltage retention noise margin, RNM, static noise margin, SNM, and write margin, WM, is also decreases, which can flip the data easily, through which the stability of the memory cell decreases. To overcome the instability of memory we design some write and read assist technique through which we can work on low supply voltage without impact the performance of memory cell. For low leakage we generally use multiple threshold transistor, decrease the rail-to-rail swing of memory cell, and dual power supply through which we can reduce the standby mode current and leakage power dissipation in 6T SRAM cell 4. As we are increasing the number of transistor on the system on chip, SoC, then power dissipation is considerable in both active as well as standby mode. So to reduce the leakage we need to reduce the supply voltage as we discuss above. For standby mode or hold mode we need to reduce the leakage of memory cell by reducing the supply voltage of system on chip, SoC, in standby mode. Conventional 6T SRAM cell. Basic or conventional diagram of 6T SRAM cell is shown in Figure 1. In this memory cell we used bistable latch which used to store or retain the data. PMOS is used to pull up, PU, the voltage, and NMOS is used to pull down, PD, the voltage. Another 2 NMOS pass transistor is connected which is used to read and write the data into or out the bistable circuit. Pass gate, PG, is connected through bit line, BL, and bit line bar, BLB, and gate of pass transistor is connected to the word line, WL, as shown in Figure 1. In most cases SRAM cell is made with less size to increase the density of SoC and reduce the cost of chip. Because SRAM contains 20 to 30% area of chip which is significantly very high. Basic architecture and operation of 6T SRAM cell. Through 6T-SRAM cell 3 operation like memory read, memory write and retention mode can perform. But the operation depends on the sizing of transistor because the same transistor is used for memory read and memory write operation. The operation mode of memory cell are as follow. Hold or retention operation. Read operation. Also bit line load increases which slow down the access time of read operation. Cell stability is critical parameter, so pass gate typically weaker than pull down transistor. A hold or retention mode of operation. In this mode of operation the memory cell is retain the data up to some high value of noise is affected the data. The maximum value is required, after that increasing the value or adding some noise flip the memory cell. That value is called retention noise margin, which describes the stability of retention mode. The circuit of retention mode is shown as figure 2. When the bit line, BL, and bit line bar, BLB, is floating or connected with high voltage and word line, WL, is put on 0 voltage, in that condition memory cell will store its data. See write operation. In figure 4 write operation of memory is shown. For write operation, pull the bit line or bit line bar at 0V through word driver pulse, which is controlled by write signal WR and WRB, and now put word line, WL, from low to high, 0 to VDD. Bit line starts to discharge and try to pull down the node 1 via pass gate. At the same time pull up, PU, transistor tries to through pull up and pass gate transistor. We make powerful write driver and pass gate which avoid the condition of flipping. B read operation. Fig 3 describes the read operation of 6T-SRAM cell. Initially charge the BL and BLB up to the VDD. After charging the BL and BLB, put it floating and rise the voltage of word line 0 to VDD. Then both the pass gate, PG, is connected to the 0 and 1 node. So node 0 starts to charge through pass gate, PG, and BL starts to discharge, so I read current flow from BL to node 0 through pass gate. BLB remains at high voltage VDD, it discharge a little bit due to leakage, but we can ignore that discharge. The discharge rate of bit line depends on the capacitance of bit line of memory cell. If large number of column is used, then bit line capacitance will be high, so discharging of bit line will be slow. The developed difference between bit line and bit line bar is sensed by the sense amplifier and evaluate the output. For proper read operation, the sizing of pass gate and pull down transistor is very important. The size of pass gate should be less than the pull down transistor. If we will put large pass gate, then high leakage current will flow through pass gate and previous circuits problem. Description. Conventional retention mode. In this section we discussed about the conventional retention mode operation. From the circuit figure we can analyze easily that the stability of the circuit is very high and data is flipping at a very high retention voltage, but from the figure 7, we can analyze that the leakage current, like subthreshold current, bit line leakage current, array leakage current and gate leakage, is very high in standby mode. Through this circuit we cannot reduce the leakage current in standby mode. To reduce the leakage current in standby mode we need to decrease the rail-to-rail swing in retention mode 8. Diode connected virtual ground retention mode. As we discussed in previous section, leakage current is very high, so to reduce the leakage current in standby mode need to reduce the rail-to-rail swing in retention mode. As figure 11 shows, the source bias replaced the ground voltage of this circuit. For source bias we used a diode connected NMOS, which is controlled by the enable N signal, means when N signal is high then it works in read or write mode. But when N signal is low then leakage current passes through the diode connected NMOS and PMOS. Stability of the memory cell is decided by the rail-to-rail swing of the memory cell 6. Rail-to-rail equals VDD virtual. Lower the value of virtual, more the stability of the memory cell, but same time less reduction in leakage current. So for proper virtual ground we used the combination of PMOS and NMOS for better cross corners, because if we used only NMOS for virtual ground, then SF corner will be worst, because for SF corner PMOS is fast and NMOS is slow. So for proper process corner we used the combination of PMOS and NMOS. Bit line and bit line bar will be floating to reduce the leakage current through that. With the combination of PMOS and NMOS we can get the good process corners, but the stability at SF corner is not good. We can analyze from the figure 13. Stability of the memory is decided by the sigma qualification. Sigma is the ratio of RNM and standard deviation. As compared to the previous circuit, leakage at standby mode is reduces, but the stability at SF/40 and SF/125 corner is not up to the mark. SF/40 is most unstable point, and at FF/125 highest leakage current in standby mode. This is due to the virtual ground voltage is controlled by the threshold voltage of the NMOS and PMOS. Threshold voltage of the device is increases as we decreases the temperature, and as we increases the temperature threshold voltage is reduces. So the stability is less at less temperature compared to the high temperature. Proposed architecture. As we discussed the problem in source bias circuit, the stability at SF/40 is worst and the leakage current at FF/125 is maximum. So to overcome these problems we designed an architecture in without diode connected NMOS and PMOS. Here we used a simple NMOS whose gate is controlled by some other circuit which is described in the figure 15. With the help of this circuit we overcome the problem of instability at SF/40 and SF/125 corners. 4096 MEM cell. Reduce the leakage and increase the stability of the memory cell in standby mode. Results. Fig 17. Stability of memory cell in terms of sigma qualification. The stability of the memory cell is improved by the proposed circuit. As we can observe from the figure 16, the stability at SF corner is worst in previous case, which is improved by large amount is new proposed circuit. Also the leakage current is reduced by 5% at FF corner as comparison to previous circuit. Fig 15. 6T-SRAM with virtual ground and variable gate voltage. For this variable gate voltage we used another memory cell which is higher than the 4192 memory cell, so that leakage will be more as compared to the 4192 memory cell, so gate voltage will be higher than the drain voltage of that memory cell. As we increase the gate voltage by some microvolt as compared to the drain voltage, the strength of NMOS is increases, which will put the drain voltage towards ground end. Fig 16. Variable gate voltage. Memory read. Proper operation of memory read. We need some read assist techniques because in 6T-SRAM cell, we need same path for read and write operation. If we sized the memory transistor, either we can improve read or write of the memory. If we improve read margin of the memory, then we will lose the write margin and vice versa. So to overcome this problem we need some read and write assist technique for proper operation of memory read and write. Read assist techniques. Dual power supply. Word line underdrive. Reduced bit line capacitance or use shorter bit line. Sub-VDD bit line precharge. Due to several advantages and disadvantages of the read assist, we used word line underdrive technique for read assist. Dual power supply. In dual power supply SRAM, we used two power supply, on for memory array power supply and second is for peripheral. In SRAM most of the leakage power of static power and dynamic power is dissipated by the peripheral of SRAM, so for low power consumption peripheral is put at less voltage as compared to the memory array voltage 5. Word line selector row decoder is also put on memory array voltage because row decoder drives the word line of the memory array. As in figure shown, the power supply of memory is VDMA and power supply of bit line is VDDMP. For less power consumption peripheral power supply is less than the power supply of memory arrays, VDDMP VDMA. But it is very difficult to generate dual power supply on SoC. So generally the scheme is less in use, but if we need high speed memory then this scheme is best because in other scheme performance loss happened. Word line underdrive. Word line underdrive is most famous concept for better read margin. In this scheme we reduce the word line voltage which is connected to the pass gate of the memory cell. So, Decrement in word line voltage. It will decrease the strength of the pass gate and improve the read margin or static noise margin, SNM, of the 6T memory cell. Word line is decreases by some delta V voltage with the help of WLUD circuit. COR responds to this changes in the circuit. The static noise margin of memory is improved by God amount because we reduce the strength of pass gate and improve the strength of pull down transistor 5. As for low leakage and less power consumption, we need less power supply, but as we will decrease the power supply, SNM also decreases. So to improve SNM and D dynamic noise margin, DNM, word line underdrive, WLUD, scheme is very helpful. Through WLUD flipping time of memory cell is increases, which reduces the data loss at low SNM and DNM. So with the help of WLUD probability of losing the data reduced. To increase the read stability of 6T-SRAM memory cell proposed the architecture which is shown in figure 20. In this figure we used a NOT gate as a word line driver with high strength of PMOS, which is followed by WL6T-SRAM memory cell is a single port memory cell. It means used a single path for both read and write operation. If we want to improve the read stability, then needs to decrease the strength of pass gate and increase the strength of pull down transistor, whereas for the write stability need to increase the strength of pass gate. So this is contradict between read and write stability in case of single port memory cell. To overcome this problem we designed an architecture to improve the read stability without impacting the write stability of memory cell. In this architecture we decrease the strength of pass gate during the read operation of memory cell, through which will increase the flipping time. Within this time we can read the data without flipped it. Proposed architecture to improve read stability. To underdrive the word line we used a PMOS, but the worst corner corresponds to FS/125. At this corner high underdriver is required and at SF corner no underdriver is required. So to underdriver the WL we need a process compensation circuit through which we can control the bleeder voltage of PMOS. For process compensation we designed one PMOS. With series of 2 NMOS, by adjust the size of transistor we can produce the voltage as per requirement. The process compensation voltage is shown in figure 22. So from figure we can look that the voltage difference at FS and SF corner is high, but still the value is high at FS corner. So reduce this high value we require a subtractor which will subtract all corners values, and by using NMOS we can put the drain value of PMOS at 0 volt. So through PMOS subtractor the value at FS corner reaches to few MV value, which is enough to underdrive the value at FS corner, and also used a temperature compensation circuit through one NMOS and one PMOS connected in diode fashion. The output of the circuit is equal to the threshold value and took the benefit of threshold voltage with variation of temperature. As we decreases the voltage the value of threshold increases, which more underdrive the WL at higher temperature. Variation of WL with process corners is shown in Fig. 23. Results. From the figure 22 we can observe the process variation. The strength of PMOS is high for SS and SF corner and low for FF and FS corner, so the voltage value is high in case of SF and SS corners, and strength of NMOS is high for FS and FF corners, so value is low at these corners. In figure 23 we can observe the underdrive of WL and per requirement, which is varied on process corners. Corresponds to the worst case at FS/125 WL underdrive is maximum and SF/40 WL underdrive is minimum. So the requirement is matched with the help of new circuit. Memory write. Negative bit line technique. This is most popular technique to improve write margin of memory cell. In this techniques we improved both write failure like less D.C conditions, or improve the strength of pass gate by increasing the D.C voltage, and also increase the time slot to improve write failure due to less time slot. By using the strong write driver put the bit line to ground and then turned off the write driver. After that by using capacitor can put the bit line below the ground level by using the concept of capacitor. I.e. capacitor tries to oppose the sudden changes of voltage across it. So as we sudden change the input voltage, WR, of capacitor from high value to low, capacitor tries to oppose the change of voltage and gives negative bump at output of capacitor, which is bit line or source terminal of pass gate. By using this negative voltage improved the strength of pass gate as compared to pull-up transistor. The strong pass gate makes the fast discharge of node 1, which helps to improve write margin of memory cell. Lowering of memory array voltage. This technique used to improve the write margin of the memory cell by decreasing the strength of pull-up transistor as compared to the pass gate. Node 1 try to discharge through pass gate for successful of write operation. If the strength of pull-up transistor is high as compared to pass gate, the node 1 never goes to ground, which result in write failure. Due to the high strength of pass gate, discharging through pass gate is high as compared to the charging of pull-up transistor, so node 1 discharge fastly through pass gate and write operation happens successfully. Rising of memory array ground voltage. By increasing the voltage of memory cell rather than putting on ground is another way to improve the write stability of memory cell. In this technique, rise the voltage of memory cell by using transistor as a resistor, so the voltage of virtual ground rises, and due to high strength of PD transistor, it transfers the voltage of rises virtual ground voltage to node N0 its mean drain voltage of PU transistor, so the strength of PU transistor decreases without compromising the strength of PG. So now the strength of PG is high as compared to the strength of PU transistor and can write the data without write failure. The systematic arrangement of this technique is shown in Fig as below. These above techniques show the behavior of write assist circuit which require during the successful operation of write at low voltage. But the other hand, due to word line underdrive or to improve read through read assist circuitry, write operation is not happening properly, so to avoid the conflict between read and write operation, use the assist circuitry simultaneously, which improve write as well as read operation of memory cell. The leakage, read, write operation and also cost is improved. Assist techniques benefits is described in 13. As voltage is reducing in case of WMA, assist techniques is required, or when combined operation means read and write operation is going on simultaneously, then some assist technique is required. 14. Due to reliability issue at high voltage can be improved by using two-phase scheme at low voltage. 15. Another technique is used to improve the write margin at low voltage is capacitive coupling. 16. In this scheme, initially BL discharge to ground through write driver and the input of capacitance is kept at pre-charge state. The pre-charge voltage starts to discharge to ground, the negative voltage meet at output of capacitance, which increase the write current through pass gate. But at high voltage reliability issues occurs due to high negative voltage at source of PG and the voltage increase even high as compared to supply voltage, which decrease the life of memory and also can break down the thickness of oxide or increases the stress level at the gate input of pass gate. The failure of dielectric oxide is described in 1718. Reliability issues and improved circuit at high voltage of negative bit line write assist. As technology is shrinking, more and more transistor can accumulate on single die, but the problem occurs due to static leakage increases as compared to dynamic leakage. So to decrease the static leakage we need to decrease the supply voltage. But due to decreasing the supply voltage, stability problem arises in memory, and stability also decreases due to conflicting of memory read and write operation. So to overcome this problem and increase the stability of memory cell we require some assist techniques. To improve the write stability, generally we used negative bit line write assist technique, which increases the strength of pass gate as discussed above. At the BLR and BLL used strong write driver to put either BLR or BLL on ground, and also used a transistor which works like a capacitor to give negative bump at source of pass gate to increase the strength or for successful write operation. So as we increase the voltage, the negative bump given by capacitance also increases, which put the gate voltage of PG even higher than the supply voltage, which is undesirable, or increase the stress level of PG, or even can break the oxide thickness with such a high electric field. 14. Or decreases the life of a transistor. Also, if we increase the voltage, more negative bump at the output of capacitance, which slow down the speed of write operation at high voltage and also increases the dynamic power. Time-dependent oxide. 13. Also dependent on temperature, means when we increase the temperature there is a high chances break the oxide at given time frame as compared to lower temperature on same voltage. Leakage also increases at high voltage due to large negative voltage at BLR or BLL, and there may be chance that it can on the unselected memory cell column or increase the leakage due to rise in voltage VGS of PG unselected column. During write operation at low voltage there is a need of extra assist circuitry, but as we increase the voltage no need of assist circuit or depend on the read assist WLUD. Conclusion. We designed a low leakage circuit to decrease the leakage current of 6T-SRAM memory cell. The leakage current decreases from 0.25 to 0.22 picoamp, as we can see from the figure 18. And also the stability is improved at SF/125 corner. Read stability is also improved with the help of proposed circuit. The strength of pass gate decreases as per requirement of process variation, and WL under drive voltage value is matched with the requirement value, and performance like dynamic power improved by 1.5% as compared to previous circuit.